So what we will do in this Zoom session is we'll quickly go through the examples that we have discussed in the last Zoom session, as well as in the recorded video lecture, which were the exercises that were given, and then we will move on. So what I will do is now I will share my screen and I'll go to the notebook mode. Yes. Someone has a question? Okay. So I'm going to move to share screen mode, right? So maybe I'll also switch off this video, turn off the video so that I could keep it horizontal. Let me check this is 100%. Okay, fine. And then it'll go to the draw mode. Right. So let's start with the 1D Fourier transform. Can anyone quickly tell me the definition for 1D Fourier transform? What was the variable we were using? We'll go through 1D Fourier transform. Continuous time Fourier transform, of course. So f of x is equal to integral over, what is the integrand here? Hello?
Kx.
Kx, varying from?
Minus infinity to infinity.
Minus infinity to plus infinity. F of kx is the kx ky space we are writing. So we are writing it as f of kx into exponential of j times 2 pi kx into x and integrating with respect to dkx, right? That was the synthesis equation. And then this Fourier equation in the frequency spectrum, we are writing it as where now the variable we want it in terms of kx, so you would be varying x, and then you start with the original function in the spatial domain f of x, then complex exponential conjugate will be there, so minus 2 pi kx into x. You need to get it in terms of kx, so you integrate it with respect to x, right? These were the definitions. Then what we were doing, we were taking a look at some of the examples. What was the first one example that was given in the recorded video lecture? What was the name of that function?
Recto function.
Right. What? Right. Good. So it is referred to as box function or rect function. How does it look like? You have just 1D variable here. So its value is 1 from x equal to?
Minus half to plus half.
Right. From minus half to plus half. This is 1. Outside it is 0. So what would be getting as a result of this in the Fourier domain now? So this is what you have as this rect function here. So for rect function, if you take the CTFT of it, what would we get here?
Sinc function.
Sinc function, right? How is sinc function? There are a couple of slight variations in the definitions of sinc function. What do we mean by sinc function here? Sine of
x by pi.
right, sine of pi x by pi x. Okay, everybody should be very comfortable with even if I give you, for example, sine pi by 4x by pi x, how to draw it, what would be the maximum magnitude, should be everybody should be comfortable with it. So practice that. If you are not comfortable, this is anyway you have it in your DSP course. So is this function symmetric? Is this function symmetric? Yes. How can you say sine is an odd? Here you will get sine of minus pi x as minus sine pi x, and there is one more negative here, so that would make it even function, right? So this is what you get as sinc of x. What's the maximum value here? What's the maximum here?
1.
1, correct. So this is at 0. What would be the value here where it is getting 0? Sink of, I should have written this, what instead of x, what should I write here? Sink of,
kx.
yeah, that's right. Sink of kx. Because we are in the frequency domain. So let me do the same thing here. Sink of pi times kx by pi times kx. Now I would call it as kx. So this value here is, at this point is
1.
yeah, right. All integers, it would become 0. This would so on. Yeah, it should be symmetric, although it is not symmetric in the way I have drawn, but it should be ideally symmetric, right? Now, if I ask you, the second one would be sink of x. What would be the CTFT now for a sink of x?
Rectangular. Box of kx.
Very good. Box of kx. See, all you need to do is whichever is there on the right side, if that function, you flip that function, and for that, whatever is there on the right hand side would be your CTFT. So once you compute one pair, other pair comes for you for free, that combination. In this function, sink of x being even function, so even if you flip it, you get the same thing. So you are getting a box function now. Now the variable being in the frequency domain, you are changing the variable from x to kx, correct? So third one, delta of x, what was the CTFT of it?
1.
Right, good. So I don't think I need to derive this because you know it from your earlier courses itself, right? Then for one, what is the CTFT?
Delta of kx.
Very good, delta of kx. So here the nice thing is that 2 pi also, that multiplication factor also goes off. This one anyway, if you are flipping it, that was still 1, right? So you have the delta of kx nicely. Then the other one we had a look at is e power minus pi x square. So what did we say about its CTFT? E power?
E power minus pi kx square.
Right, good. Is anyone having a problem in deriving this, or every one of you found it? If every one of you found it, I could skip it. Otherwise, we would go through it quickly. Do you want me? Does any of you want me to quickly go through it?
Yes, sir.
Okay. So what we need to do now, we need to find out the Fourier transform for this. This would be variable for us is x varying from minus infinity to plus infinity, e power minus pi x square multiplied with e power minus
Minus
j.
j 2 pi
2 by x.
kx x
Right. Integrated with respect to the variable dx, right?
dx.
So how could I write this out? E power minus, I can take pi also out. This would become x square. Then what? What will be this? X square?
Plus j 2k x
Right. Right. Plus 2 times
j
j k
kx
subscript x into x. That's what it is going to be. So can I now write this as x is varying from minus infinity to plus infinity, e power minus pi of, so this you want to write it as just a square term and another subtract it from the other term kx, because that is something I could take out because the integrand here is with respect to x. So what the way I would like to write here is x plus what would be the other term, so that I will get a square plus 2ab plus,
jkx
very good,
jkx
j subscript kx, good,
whole square
whole square minus what?
pi kx square.
Pi anyway I kept common here.
Okay. Plus no
Minus na?
kx plus kx square. Kx square.
Minus kx square, right?
No sir, plus will come sir.
Yeah, you are right. Plus kx square. That's right. That's right. It's because j square is there, na? Very good. Yeah. Kx square integrand with dx. Now can I take this term out? Yes,
Yes.
I can take it out. So that would bring me e power minus pi kx square into, let me call this as something as y. Okay, I could do some other complex number y, e power minus pi y square into, even if I call it as y,
dy.
integrand, yeah, this will be still dy. This y is varying now from minus infinity to plus infinity. This is something you would have come across in multiple places, right? And earlier also you would have come across this. So for example, let you call it, let I equal to, uh, it's just change of variable. So I am just reusing x also. I could have written this where x is a complex variable there. X need not be, yeah, x need not be as such a okay, the variable doesn't really matter. So if you want, you use z something else also, minus pi x square into dx. I could also write it as y varying from minus infinity to plus infinity, e power minus pi y square into dy. So I take I square now, I am multiplying it. Hope you understand the trick I am trying to do here. See, while I have something in the rectangular coordinates varying from minus infinity to plus infinity, see, if I am varying first for a fixed value of x
Sir,
here. Yeah,
sir,
yes,
we
sir.
can simply tell that this is a PDF of a Gaussian, and then we can say that its integral will be equal to 1.
Yeah, that is also fine. That is correct. That's exact. That's very good. That's also absolutely fine. So this is a yeah, I agree with that. So even if you are doing it, let me also quickly do it this way. See, for example, the way we are trying to visualize it is, you are having, so I square would be, let me first write this out. X varying from minus infinity to plus infinity. Oops, I don't know. Sometimes this happens. Okay, minus, okay, I'll better I write it, e power minus pi x square dx, that's equal to e power minus pi y square dy. So I square, if I multiply, x varying from minus infinity to plus infinity, y varying from minus infinity to plus infinity, exponential of minus pi into x square plus y square into dx dy. Now look at how it is there. Suppose you take a particular value of x, then this whole thing you are going through, right? Minus infinity to plus infinity of, so this is your y value. Okay, so you need to cover the whole space, right? That's what you are doing. So another way is, if you are looking in terms of the polar coordinates, what you could do is, same space you could also represent as saying you vary this r value, and for each r value you vary this theta value, right? Then your limits will become, r limits will become 0 to infinity. So then e power minus pi y square 0 to infinity, you could write it out. So that's the basic trick. So what you do now for going from rectangular to polar, x equal to r cos theta, y equal to r sin theta. Then what is dx dy? Anyone remember by any chance? Dx dy for this?
minus r.
No, no sir. Any other one? This you should be getting, I think, in your EMF course. You will be doing some transformation similar to that, if I am not wrong. This is a very standard one. This is a standard change of integrals you would be doing.
Sir, something like r sin theta, dr d theta.
Yeah, very
Minus
close.
r square sine 2 theta by 2 d theta.
No. Anyone else? Any other guess? This would be equal to r dr d theta. Just check this out. This is very standard one. So basically, if you wanted the formula wise, typically what you would be doing is, you have two variables now, r and theta, both are there mixed together. So dx will be, if I am not wrong, you would be writing something like dou x by dou r into dr plus dou x by dou theta into d theta. Similarly, y is also a variable of 2. So you would do now dou y by dou r into dr plus dou y by dou r into dou y by dou theta into d theta. So something like this, you have to use this formula, okay, and use it. This is a very standard one, so you just Google it, you will find different proofs also. If you want some intuitive graphical explanation, that's what probably I'll try to give it quickly. This is you should be getting it in EMF somewhere, if I'm not wrong. So assume that this is your x and y. Okay, so let's say this is your r value. Okay, now you are increasing it this by dr here. Okay, now assume that this theta whichever is there, this also you are increasing it by d theta here, right? Now then essentially your this is what would give you the area now. Okay, that's what you need to find out when you are saying changing the ones. So this would be equal to, when theta is small and dr is small also, this is something like you could write it as r times d theta, and this area I'm giving you some intuitive one, this is not the rigorous one, but you could find it out. Just dx dy, the otherwise originally you draw in a similar lines for dx dy, and then if you come here, this would be equal to r times dr d theta. This is some intuitive proof. Okay, but again, you just Google for it, you will get more rigorous one if you want. This is the standard one. Okay, I right now for the time being I am directly using this. So my I square would be equal to, now what would happen with this, your theta would be varying from 0 to infinity, sorry, 0 to 2 pi. You are varying the theta from 0 to 2 pi. R would vary from 0 to infinity. And here you have e power minus pi times, what do you get there? Minus pi times,
R square.
right,
R
r
square.
square, and dr d theta. So d theta you could take out, right? You vary it from 0 to 2 pi, that would give you 2 pi. Then what is the integration for just r here? Anyone
E
can
power
quickly?
minus pi r square by 2.
Very good. E power minus pi r square by
2.
2 or something else?
2 pi.
Very correct. It's 2 pi. Oh, this r is taking care of this again coming, whatever is coming to r, right? This will be 2 pi. So then is that all or something else? E power minus pi r square by, still something is missing.
So limits from 0 to infinity.
Okay, that's there. Still something is missing.
Minus.
Right, minus 2 pi. So now what could happen? This and this would cancel. Now this would be equal to, if you are applying the first, I don't know why it is suddenly giving a trouble. I cannot go back here. Just one minute. చేసాను ఆల్రెడీ. ఇందులో చూపించు, అందులో అందులో చూపించి ఉంటుంది, వాళ్ళకి పంపించింది ఉంటుంది వైహిత్, అందులో చూపి. జస్ట్ 1 minute, ప్లీజ్ బి దేర్. Okay, so here you had minus pi r square. Anyway, what was there in the top here? Something got missed here. E power minus pi r square, right? So yeah, so if you are applying infinity here, that's becoming 0 minus, and then at 0 this is 1. Anyway, outside there is 1, so this would be equal to 1. Okay, is that clear? Now I square is 1, so I also has to be 1. I don't know, suddenly the whole thing got vanished, but you know now, right? You substitute you for I. Okay, you are getting it to be equal to 1, right? Here outside, what did we take here? E power minus pi kx square we have taken out, right? So earlier one, if you remember, f of kx was e power minus pi times kx square, right, into I was there, so that was now 1. So that's why the Fourier transform of e power minus pi x square is equal to e power minus k subscript x square. Is that clear? Any questions here? Is everyone fine with this, or are there any questions here? We will
Can
anyway.
you once again repeat how you
Which part shall I
f of
repeat?
kx equal to final?
This one, huh? See, unfortunately, this got messed up here. This got disappearing sometimes. This is not working well. See here, what we did after the substitution. So what we did was we have taken e power minus pi. So how did we write this actually? E power minus pi kx square has come out, and inside what we had is some y varying from minus infinity to plus infinity. Okay, exponential of e power minus y square dx dy. That was what we had, isn't it? After doing the substitution.
Understood, sir.
Right. Now what we did, we considered it as I, and we computed I square. And after that, we have seen that this is equal to 1. Correct? So what is remaining is e power minus pi kx square here.
Yes, I understood, sir.
Yeah, good. Anyone else? Is there any question here? Yeah, it is. I think sometimes suddenly things are disappearing from this OneNote. I should probably update this one with the recent or something like that. Okay. So if this is fine, we'll go to the other examples. Now, another one is, for example, delta of shifting of the impulse. So these are the properties we would be discussing. What would be the CTFT of this? If you are shifting it by x, e power
e power minus j 2 pi kx x naught.
very good, kx x naught. Now suppose I am taking the other side now. Okay, so to get the same thing, what I should do, you change a sign of it, change a kx to x and x to kx, and also change the sign. So you would be getting here e power j times 2 pi times, okay, and that you want k to be constant now, right? Because this is a function of x, so you made it as k naught. Now, what would be the CTFT of it here? Delta of?
Kx minus k naught.
Right, good. Kx minus k naught. Then, so next one. Yeah, let's say this is 7th. Now, the next one is I have cosine functions now. I'm slowly coming into sinusoidal functions here. 2 pi chi naught into x. So how do you compute the CTFT of it from based on the functions that we already computed? How do you write cos now?
E power j 2 pi
Sum of
kx
exponentials,
plus
Right.
yeah
So what would be the answer now?
complexes.
So
What would,
j
half
half
times e power
Half
j
of
e power?
e power j 2 pi kx k naught x.
Oh yeah. That's how you write on this side. In fact, right? Half of e power j 2 pi k naught x plus e power minus j 2 pi k naught x. That's how you would be writing on this side. So now that would result in here, this 1 by 2 would remain same. E power j 2 pi k naught x, you would make use of this property. Okay, so I could, for example, write it as, so if I'm taking this one, let's say just first I could see it in any, again, yeah, I think it is disappearing. That's kx plus k naught,
Plus k naught.
right? Plus delta of kx minus k naught. Is it not? Now, I would like to do now same thing for sine now, let's say. For sine of 2 pi k naught x, if I want, how do I write it here? 1 by 2j, right? So that would be minus j by 2, correct? So let me write it as j by 2, and internally let me change that. That would give me e power minus j times 2 pi k naught x minus e power j times 2 pi k naught x. Am I correct? So that would give me the CTFT will be e power j by 2 into delta of kx plus k naught minus delta of kx minus k naught. Is it not?
So it should be minus j by 2, right?
Minus.
No,
No,
sir,
what
it's
I
correct.
did is I just took the j negative side inside.
Oh,
So
okay. So minus kx minus
minus
k.
j.
Okay.
So is it fine? So just let's put the how it looks like here. And it's anyway 1D. We could draw it. We have kx, right? So this is your f of kx. Where first of all, where is this value impulse at? Assuming k naught is positive, where will be that?
Minus cannot.
Right, minus k naught. What would be that? Multiplied minus k naught. This will be multiplied by j by 2. And another will be at k naught. Again multiplied by j by 2. Is that correct?
Minus j by 2.
Right, minus j by 2. So yeah, I should not be drawing complex numbers like that, but assume it's only, yeah, this is not very proper, but we assume just I'm showing it.
You can plot magnitude spectrum only, sir, and phase
Sorry?
spectrum are different. We can plot magnitude spectrum differently and phase spectrum differently.
Right, right. That's how I could plot it. So I assume that one way is magnitude and phase spectrum. Otherwise, I assume that I am plotting real and imaginary here. That's also is fine. So I assume that this is the imaginary part I am plotting. So then what would happen here? This would be, yeah, those things got again. 1 by 2 is there here, right? Sorry, j by 2 is there here, delta of that. Okay, so this is at k naught. I had here minus 1 by 2. If I write it as 1 by 2, what I am plotting here is imaginary part of, to be more precise, f of kx. If I am plotting it, this is how it looks like. Or yeah, if I'm, another word is magnitude phase, I could ask you to draw magnitude and phase also. Then magnitude both will be 1 by 2. Phase would be, you need to modify the phase part there. The one is right. Is it clear? So the other one was, what was this symbol for? I'm using.
Impulse train.
Right, this is an impulse train. This is also referred to as Shaw function. They would be referring to it as Shaw function. And anyone remember any other name for it I was referring to? Anyone remembers that name? One more name I was, sorry, I was mentioning. No, it's a comb function. Yeah, direct comb, right? Correct, that's correct. So if you plot it, you could see it looks like the like a comb here, right? That's why they refer to as Shaw function or direct comb also, correct? Okay, so this, how did we define this out? This is equal to I varying from minus infinity to plus infinity, delta of x minus I. Any idea on what would be the CTFT of it?
Impulse train only, I think.
Impulse train only, that's correct. Let me write it as I varying from minus infinity to plus infinity. Then what here? Delta of?
Kx minus.
Minus I.
That's right. Delta of kx minus I. So how could I write it? This is nothing but comb function or Shaw function, okay, or impulse train of simply kx. Notice here, if you recollect from what you have seen with DSP, it's equivalent to 1 by the spacing would come if the spacing is different. This being 1, spaced equally spaced with 1 by 1 also would give you the same kind of comb function here. Because x is, you are taking this at 0, 1, 2, 3, and so on. You are getting the same thing here. Okay, is it clear so far? So with that, I think we will now move on to the 2D part now. So let's go to 1 minute. Okay. Two-dimensional CTFT functions. This definition also we covered in the video. So now what we would do, instead of using f of x comma f of x, we would now go to f of x comma y. How is it written now? How do we write it now? Integral over kx is varying from minus infinity to plus infinity. Ky from minus infinity to plus infinity. What should I have inside?
F of kx ky.
Right, capital F of kx comma ky multiplied with exponential of
J2 pi kxx plus
J2 pi.
kyy.
j2 pi times.
Kxx plus kyy.
Right, good. Ky y integrated with respect
Pkx
to.
dy ky.
Very good. Right. So let me now write the Fourier transform also here. Kx comma ky is equal to x varying from minus infinity to plus infinity, y varying from minus infinity to plus infinity, f of xy into exponential of
Minus j pi j2 pi kxx plus kyy. Dx dy.
That's it. Right. Now there is something called as 2D box function. So earlier was 1D box function. This is referred to as, I'm looking at now few more examples here. So first I'll see examples, usually the extensions of 1D to 2D. So 2D box function here. Can you guess how it would look like now? 2D box function, what it means? Based on 1D box function, you tell me
Cuboid.
now. Hmm? What could I expect here?
Cuboid.
Sorry?
Square. Or cube.
No, I could not hear properly.
Cuboid, sir.
Cuboid. So can you tell me the formula? So I would call it as delta, since it's a 2D, maybe again this box symbol is I'm using, since it's a 2D, I'm just writing 2 there. Of course, the moment I give 2 variables, that should be good enough. So how does it would look like? What is your guess now? How is it defined?
One for x from minus 1 by 2 to 1 by 2 and y
Mm-hmm.
1 by 2 and mod y less than or equal to
Mm-hmm.
1 by 2.
Mm.
Otherwise 0.
Zero
Good.
otherwise.
Okay. Now I use, for example, this as one color and this as 0 as 0. So as an image I want to plot. So how does it look like now here?
Cross, like a cross.
Is it a cross?
Like
Plus
a
plus
square patch on the image.
Exactly. So this whole region is equal to, this is equal to 1 by 2. This is minus 1 by 2. This is again on y 1 by 2. This is minus 1 by 2. Inside its value is 1. Outside it is 0. Can you now tell me what would be the CTFT of it? Anyone? Two-dimensional CTFT. I will skip even 2D from now on writing, because anyway this would tell you that this is 2D. So anyway, for the first time I'll write. Can you tell me what would be the CTFT of it? Before that, let me ask you this question probably, then the
sync
answer will.
kx into
Okay,
sync ky.
very good. Sync kx, very good, excellent, into sync ky. Okay, we'll see why is it so. How could you write this function now? Can you write separate? Is it separable basically? Can you write it
Yes, sir.
as a combination of two 1D box functions?
Multiplication.
Right. So 1D box function of x, okay, and another box function in the direction of y. Is it not? Look at how I am writing it. Abba. Again, this got there erased, but it's okay. So this is, for example, your -1/2 to 1/2 here. This being your delta of x. Okay. Now the other one is if you want x and y. Okay. So y, if you want to plot, yeah. Now you just consider that this is my, since this is y, okay, I'm just considering this as y, and this is where I am plotting. Okay, so that visualization wise it would be easier for you. Is that correct way of drawing it, or how should I draw it to show it?
With
So
third
the
axis.
magnitudes are along z-axis, right?
Right. So no, I'm just thinking -1/2 to +1/2. Okay. So where did I? So this is what here I would like to write out here. So what would happen then? For example, if I'm drawing like this, okay, from y, is that not correct? If I'm taking, I'm just writing this pi of y. Is it required basically? Yeah, I think even more than,
During plotting, sir, we will take x-axis and y-axis, and in z-axis we
yeah,
have to take.
that's better than this
And
multiplication.
y-axis is 0 in pi x, and
Right, correct.
x-axis is 0.
Yeah, that's easier to even then. Yeah, this unnecessarily complication. So you think about it in this direction. So for example, you take x -1/2 to +1/2 when you are here. This is 1. Similarly, for this, anyway, it cannot. It has to be. If it has to, it's like a AND gate, right? This has to be 1, and the other one also has to be 1. This would happen only in this region when y is equal to -1/2 to +1/2 only it would happen, because you are having row of y. Okay, this you are varying. Similarly on this side, this is 1 for the whole region here, but the other function rho y is 1 only for this region when it is going to be -1/2 to +1/2. So essentially then you are getting a box here in the center. So probably the name box function makes a better sense when you look at this in 2D, for a 2D function rather than the original 1D function. Is this
So,
yeah, yes, Shashwat.
so like in pi x of x, the box function of x, like for all the values of y, this thing is being extended out, right?
Right, correct. See, for pi x of x, what would happen if I just draw, see, if I just take pi x of x, so then what would happen from 0? So this is all equal to 1 here for all these values, where you have, for example, here -1/2, here 1/2. This is your x. Okay. For all the, whenever I am drawing lines, you think that is equal to 1. Now, pi y is what's happening. It is 1 only for all these values. Okay. Where your y is, for example, this is 1/2 here on the y axis. This is your y axis. And this is 1 for all these values here. So if you look at the commonality, only during this, both pi x and pi y are 1. So only this region would come for you when you are multiplying them.
So,
Is it making sense?
yes, sir.
Okay, good. So I think we could generalize it and look at it as, for example, if f of x comma y is separable, then what we could say is you could write f of x comma y as some one-dimensional function. Let's call it as f subscript x of x, and another function f subscript y, which is a function of y. So in that case, your f of xy, the two-dimensional CTFT would be equal to your one-dimensional Fourier transform of this, right? And multiplied with one-dimensional Fourier transform of this ky, right? This is essentially, we are just putting it in a as if a generalized one that again comes from this equation. You can derive this from here. So the case we are considering here is, or you could consider here, the both are fine. Okay, so your f of xy, you could write it as, let's say, fx of x multiplied with fy of y. Okay, now this is a 1D function, this is a 1D function. This you could write it as, you could separate it anyway here, e power minus j 2 pi kx into x multiplied with e power minus j 2 pi ky into y, isn't it? Now all you do now is you take these two together and the other two together, and then you separate this dx dy. Then they are nothing but, this is nothing but definition of one-dimensional continuous time Fourier transform. Is everyone able to see this out? Whatever property we have written here, it's essentially coming from this definition itself here. This is anyway exponential is separable. The moment it is separable, you could write these two integrands separately. That's all. Is everyone able to follow that? This is a very important property. Good. Any questions so far? Okay, good. So then I'll go to another, after this box function, other example I'll take a look at is e power minus pi of x square plus y square. Can you tell me what would be the CTFT of it? Now it's CTFT of it.
E power minus pi kx square plus ky square.
E power minus pi.
Kx square plus ky square.
Good. So can you say anything more here? Why? How are you able to do it? Can you do like any?
I am separating them into x and y functions, and then
Right, and you are doing it. And again, you could see here. Can you make it as a 1D function? Is it possible to make it as a 1D function? Suppose assume that from kx,
Polar form.
right, I could actually make it something like rho x square. I could make it. See, it is same as, for example, this you could write it as e power minus pi r square. Same problem again. It has no. Okay, luckily I got it back. Okay, so you could see here that this is two-dimensional function when you look at it in terms of x and y, but the moment you see this function radially, the same function is repeating for every value of theta here, is it not? So it's like you consider its value for so along all these points where this kx square plus ky square is constant, you would be getting the same thing. So it's in effect equivalent to a 1D function when you change the variables there. Is everyone able to see that? When you are changing your variable from kx ky to polar coordinates, where you consider kx equal to rho x cos theta, ky equal to rho y sin theta, you could notice that this value in fact is not dependent on theta. It is independent of theta. Is that clear to everyone? Devian, are you fine with it?
yeah, some idea I got, but I have to see again, sir.
Okay, so you agree till here, right? See, how does this function would be till here anyway? You yourself telling that this is the answer, correct? E power
Yes, sir.
minus pi kx square plus ky square. How does that would look like? See, if I am all these values, I take a circle here. This is my kx. This is my ky. Okay. At all these points, kx square plus ky square is constant, right? When I'm taking the radius, what is the radius
Yes.
here? Assume
Root
that
of
k,
kx square plus ky square.
right? Of course, then you consider that particular way, the capital kx you consider, for example, this, and that as small kx. So at all these points, this value is constant, is it not? So everywhere this function along this radius should have, when I move to circular coordinates, it should have same value, is it not? So when
Yes,
I,
sir. Yeah.
so when I move, do this change of variable, I don't have to worry about at what theta I'm looking at, because at all thetas, it doesn't matter once you know the R value. Is it clear now?
Yes, sir.
Good. So another interesting thing also here you could observe that a radially symmetric function, the Fourier transform of that function will also be radially symmetric. This is a very important property here, for the simple reason that anyway, while you are computing here, you could simply compute its value at just 1D case. You could consider R and theta, you go, and only at R you are computing that value. That way also you could see it. A radially symmetric function, if you consider it, okay, its DTFT or CTFT also would be equal to radially symmetric function. Is everybody able to see why is it so? Hello? Is it clear for everyone? See, it is radially symmetric means any function given in x and y, you convert it to r and theta. So since it is radially symmetric, you just compute here in the r and d, if you look at, you just compute for one value of r, the theta is immaterial now. So the same thing would happen here also. So you just need to compute 1D transform there, and that it would repeat. So a radially symmetric function, if you have, and if you are trying to find out, oops, power is gone. Okay, it's still, are you able to hear me? Hello? I hope the power is there. No. Hello, are you able to hear me now?
Yes.
Yeah, there was a power cut, so I switched to mobile. Again, power has come, so let me switch back just a minute, because mobile sometimes is good, sometimes connection is not reliable. So let's just me, it is taking. So far it is good, is it? If there is any lag, you just tell me so that I'll switch back to my LAN connection. Okay. For now, I'll go ahead with my mobile connection. So far, is it good?
Yes, sir.
Okay, then I will just, let me check if I am getting, no, not yet. That modem is taking a, yeah, it's coming now. Okay, so are you able to, is it still connected, right? Hello, am I connected? Okay, okay, I'll share that. That's not a problem. Show share screen. Share it. Okay. My screen is clear, is visible right now, is? Okay, good. So this is another important property. You just pay attention here. See, if it might be a 2D function, okay, but the moment it is a 2D function, you could all, and if given that it is radially symmetric function, you could write it in terms of r and theta. Now just your variables, instead of x and y, you have r and theta. And if I tell you that this function is radially symmetric, theta is just a dummy variable there. You don't have to worry about theta, because I'm saying it is radially symmetric. For every theta, you have the same thing. So you find out for it only, as it only depends on r. And then if you are looking at the output, there the output also would be radially symmetric. Is that clear?
Sir, this is valid only if the function that we are defining in the time domain is valid for like the theta belonging from 0 to 2 pi.
No, I'm saying that this function is radially symmetric, right? If the function is not radially symmetric, this is not valid at all. See, if the function is not defined for all values of theta, it is no more radially symmetric. We won't call that function as radially symmetric at all.
Yeah, yes. Okay.
So that function has to be same for all values of theta from 0 to 2 pi. Is it not?
Yes, sir.
So,
Okay. Yes, Sumant.
sir, can we visualize it as like in one-dimensional Fourier transform, like for real and even, and the frequency domain will be real and even. So, can we?
Yeah, this, for example, I just show you some function here. Okay. Anyways, in our functions, we haven't had this. Let me just go. I thought of discussing the examples later, but let me just do it right now itself, since you asked the question. Okay, just look at this function here, for example. So this is a radially symmetric Gaussian function, and of course it's slightly bit more next level of Gaussian, where I have divided by sigma square also here. And you already should be knowing by this time that if your sigma variance is high in the Fourier domain, that gets inversed here when it comes here. So it is in the denominator. In the Fourier domain, it comes to sigma square. I wanted to work you out, give it you as an example, but it's okay. So then what would happen is your function is radially symmetric here. This is how you would be getting it. Similarly, this is another function which is called as a circular disk. Okay, earlier that what we have seen is a box function. Now this function is this one, circularly symmetric disk function it is called as. Okay, so again, just like this, what you get will be in terms of, they are referred to as Bessel functions. Okay, this is something very close to sinc you will get here, which would be decaying as you move on, and you would see that the moment you are moving in the radial directions, okay, that values all would be same here. I hope I have one more. Yeah, these are the two examples I could quickly show you that. Yeah, now is that answering your question, or is it different?
Yes, sir, it is. Like, I was just making an analogy. Like, is it like analogous to the like in one-dimensional real and even corresponds to real and even frequency domain? So, can we think it as in like analogous in 2D?
No, I didn't. Maybe the question is not very clear. So maybe you could think over it, and then if that still persists, you could ask. And at
Okay,
this
yes.
point right now, I see it slightly differently, because we are looking into extending 1D to 2D here, but this 2D function again equivalent to being 1D. That's how we are perceiving things here.
Okay, sir.
So
Okay,
just
yes, anyway, I got it.
That means in time domain, when signal is real and even in one-dimensional case, its corresponding Fourier transform is real and even in frequency domain.
okay, right.
In two-dimensional also, is it same? Am I right, Suman?
Yeah, yes, sir. Like in two-dimensional, if it is radially symmetric in time domain, I mean like in X domain, so it is the same, like the radial symmetric in KX domain also. Like, is it the analogous that I was asking?
No, it is not. Can you rephrase it a bit?
Sir, actually, the question is, I think, if if the function in x is even and
Okay, if f of x
even
is
and
even. Okay.
even and real, then the kx domain will also correspond to even and real. And
Okay.
similarly, a function y, if it's real and even, then its ky function will also be if it's like if it's real and even, then in 2D can we combine this and say that f of x comma y is real and even, then can we say that f of kx comma ky will also be real and even?
Okay, and maybe we are complicating it a bit, could be possible actually, but this is for me is very straightforward here. If you look at from the way we have seen it here, this is quite straightforward here, that there is a 2D here. Okay, just visualization also, this is much easier. So although there are two functions, this is a just a function of one variable. So what you get as an output should also be a function of one variable when you are converting from here to r and theta, right? So theta is now immaterial here. We are just using that property and saying that here rho x square instead of r, we are getting here rho x. And then this is true for any theta, this is constant. So for any theta, this should have this value. That's all here. Maybe mathematically, if you put even and odd, you might be arriving at similar equation. But here I'm not even going till there. I'm just looking at simply the way we are writing 1D becoming 2D. That's all I'm looking at here. Yeah, maybe you could think about it a bit more and then come back, Sumant, probably.
Okay, sir. Sure, sure.
Okay, so good. So if it is fine, I'll just move on to the next part. A few more examples. I guess none of you have a class now, right? So I would prefer at least covering till that cosine in 2D. If it is fine, maybe I'll take some 15 minutes more or something like that, if it is fine for you, because anyway that we discussed to some extent in the last class itself. So I would continue if it is fine. Is it fine? Otherwise, to get back the momentum, it will take a while to review and also I'll just go ahead. Okay. So the next example I would say is, let's say 1 is there here. What would be the two-dimensional CTFT of it? Delta of
x comma kx comma ky.
That's it, kx comma ky. So how is it now? Let's say again we go to the 3D drawings now. Kx ky, here you have one nail here. Okay, now of course then I could write the other way around. Delta of kx comma ky, obviously take negative also, it would be same. So I would get here 1 now. Sorry, I should be writing here x comma y, right? I should not be writing kx ky here. I should be writing x comma y. Now delta of x minus x naught and y minus y naught. Okay, so what would be the CTFT of it? What would be the CTFT of it? Any idea?
e
I
power
shifted one.
minus e power
Exponential.
minus j 2 pi kx x naught plus ky y naught.
Very good. That's all. So how does this, by the way, would look like? Assuming x naught and y naught are are positive. So let me call this as x. Let me call this as y. So where will be my impulse now? How many impulses will be there? How many impulses will be there?
One.
Only one. Where is it located?
X naught comma y naught.
X naught,
That's
Y
it.
naught.
Right. Assume that this is my x naught, this is my y naught. Okay. So here there is one nail here. That's your delta of x minus x naught. Okay. So then let me go back to cosines and sines. Cos of 2 pi times k1x plus k2y. What's the again before worrying about how it looks like in the spatial domain? So how would you proceed to compute its CTFT? How would you write its CTFT?
First we will convert into exponentials.
Right. So what? How should I write here? 1 by 2 into
E power
j
j
times 2 pi
2 pi k1x plus k2y plus plus e power minus j 2 pi k1x plus k2y.
right, correct. So that's how it is there, cosines. And then what would be the CTFT of it?
Half times
Hmm.
delta of
kx minus k1
Delta of
kx minus
k1
k1x
k1
hmm,
kx minus k1 comma ky
kx,
comma
k
yes sir
kx, k
minus
subscript x,
k1
kx
minus
minus
k1
k1,
comma
hmm,
ky minus k2
very good, good, plus
delta
delta
of
of
kx plus k1
kx
plus
plus
k1
k1.
comma ky plus k2
Yeah, I should not be closing it at
hmm.
comma
ky plus k2
ky plus k2.
k2
Correct. So how does it look like now? Assume again this is my kx, this is ky, right? So how many impulses do I have now? Let me call this as quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay. And then in which quadrants do I have impulses now? Assuming my k1 and k2 are positive.
at 1 and 3 sir
Very good. So this is, for example, k1 here, correct? This is minus k1. This is k2 minus k2. Right? There is one impulse here and another impulse here. Is everybody able to follow this? This is, for example, is having a value at k1, k2. So I went k1, k2 here. This is having a value at minus k1, minus k2. So minus k1, minus k2. This is one impulse here. Okay. It again disappeared. It didn't like those points. Okay. Is it clear to everyone there? Is anyone have a question? This is the right time to discuss, because this is a very crucial thing, particularly when you are doing the two-dimensional stuff. Okay, so this has, you have to be very clear with this. This is your kx, ky. Okay, is it clear how we are getting it? So, and suppose now you have other combinations also, when one of them is positive and another is negative, right? So now suppose I have a cosine on I have a cosine on the Fourier frequency domain. Then what kind of things can I expect here in the time domain? Right.
Impulses.
So you have impulses then here. So if so from impulses diagram itself, you should be able to now tell, for example, K1 and K2 are positive. In which direction is, so let me put two directions. Okay, let me call this as direction 1. Okay, I'm not anyway separating between going this and going this. Another, let me call this as direction 2. Can you check in which direction will be periodic in this case? Suppose, okay, yeah, I think this system got heated up, so it's disappearing things, but it's okay. So this is, I call it as 1, and this I call it as 2. Okay, so maybe it's a bit early for you to answer for all of you. So let's spend some time with understanding this cosine. Most of you, I hope, would have tried it at home. Let's take with the first a simple function in 1D, which we are very comfortable. Let's start from where we are comfortable. Let me call it as 2 pi times kx into x. Okay. So how does it look like? At 0, what is its value? This is my x. Okay. At 0, what is its value? X equal to 0.
That should be k naught, I think.
Very good. Sorry, that was my mistake. Good. Yeah. Now what is its value at x equal to 0?
1.
1, right? Now, of course, this would repeat, keep on repeating. Assume that this is one period of it. So what is the periodicity of it? What is this periodicity? After that, it keeps repeating. But what is that periodicity?
K naught.
Are you sure?
1 by k naught.
Right. 1 by k naught. How do I know that? If you want, you keep it as periodicity cos of 2 pi k naught into some x plus x naught. You need to find out the smallest f naught for which this would happen. So for that to happen, you multiply each separately. So k naught into x naught should be equal to 1. So multiple of 2 pi, if you have it, that would happen, right? Or it should be 2 pi, right? Multiple of 2 pi it has to be. So 2 pi. That means your x naught should be 1 by k naught. That's one way of looking at it. Or even simple way is this k naught into x should be 1. After that, this would repeat. So k naught into x equal to 1. That implies your x is equal to 1 by k naught. Initially, it is 0. This would repeat when this again becomes 1. That's all I am looking at. So x is equal to 1 by k naught. From that onwards, yeah, this is a very that would repeat again. Is that clear so far? This is again nothing new we discussed here, just the same thing you already know. Now let's go back to 2D. So let's call this as fb of function x comma y, which is equivalent to cos of 2 pi into kx into x plus ky into y. This is the function. Okay.
K1, K2.
Yeah, sorry, I was making repeating the same mistake. So let me call it as k naught and k1. Okay, good. Now, is it periodic in x? First question. Assume
No,
that
sir.
k naught and k1 are non-zeros, right? Is it periodic in y?
No.
So is it periodic in at least in some direction?
Yes.
Right. So then how do you say how much is the periodicity of it to say that? How do I compute the periodicity? So one is the direction, okay? In which orientation is it periodic? So that, so it doesn't want the class to be too long. It stopped there. I think it got heated up despite AC is on. Let me just.
So periodic around tan inverse of k1 by k0.
Right, that's right. So just 1 minute. Hopefully it would recover. This is what is happening is I have the Surface Pro. So what's happening is screen is getting heated up in almost no time. So that is having an impact on this touch sensor. So it is no more touch sensors are no more working. Okay. So at least audio is visible. Audio is not visible. Audio is audible, I hope. Okay. So I guess I have to wait. Yeah, nothing I could draw here. This got even, yeah, nothing is working here. The whole system got frozen, but still you could hear something, which is a good news. Hopefully okay, good. At least this is working. And then let me kill this application by going to the task manager. Should be able to see it here, right? So that's what I want to delete, right? Hopefully that should resume the services. Then is draw working now? Good. Okay. So two questions are there. One is the orientation of it. and then the periodicity of it. Okay, these are the two questions that we would like to answer. So let's start with the periodicity part. How do you know what is the periodicity of it? Just similar to what we do here. What is the periodicity of it? It is so what we inferred so far is it is periodic in certain orientation, neither in X nor in Y, but in particular orientation, in particular direction. So how do you know the periodicity of it? Can anyone tell?
So can we take one variable like k naught x plus k1y is r, and
then this is equal to n, this whole thing repeats because this is anyway 2 pi, correct? So when this becomes n, or if you want to be periodic, just the way you have taken here, you simply take k naught x plus k naught y equal to 1. Okay, that should give you the periodicity. So how do you get then the periodicity part? Let's say this y equal to minus kx, or I should be no, this is k naught and k1, right? K naught into x plus k1 into y. So minus k naught by k1 into x, right? Plus 1 by k1. This is along this line. This would be periodic. After that, so everybody next time onwards, yeah, well, let me keep n for a moment. So then what would happen? This is equal to n, okay, n by k1. So after every n equal to 1, 2, 3, and so on, this gets repeated. What I am saying is, this would look y equal to mx plus c, where this is then 1. So all I am doing is just like to compute here k naught x equal to n here, right? K naught x equal to n in case of 1D. So when your x equal to n by k naught, that would keep repeating 1 by k naught, 2 by k naught, 3 by k naught, and on. So this is, for example, if I take this whole thing, this is equal to 2 by k naught. So that gets repeated. In the similar way, k naught x plus k1y equal to n, where n is an integer, and then your y will be equal to minus k naught by k1 into x, right? Plus n by k1. Is that fine? Is everybody with me?
Yes,
Okay, good. So now this is, for example, your x, this is your y, okay? And what is this value here? Can I, so this value, this is basically this graph I am plotting. So here y equal to 0, right? So that would be y equal to 0 means I need to find out the x value. So what would I get here? 1 by,
n by k naught.
right. I'm just simply computing x intercept and y intercept, that's all. Okay. And what is the intercept here? 1 by 1 by, how do I find out
K1.
that? Put x
K1.
equal to 0, that's all. 1 by
K1.
K1, yeah. By the way, substitute n equal to 1 there because now we are looking at the periodicity itself. Okay, right. So again, a cross check you could do here by making, yeah, that's fine. Y equal to 0. That's okay for time being. Okay, let's not complicate things. Okay, so now what would be this length now? This length would be equal to
k naught square.
right, square root of k naught square plus k1 square divided by k naught k1. Now if you find out this distance, which let's call it as L, okay, that would tell us with what value it is periodic. Okay, the distance to it we could tell. And if you find out this theta now, that will tell you in which orientation is this periodic. That's it. So aren't they enough to figure out this theta and L? Given this, won't you be able to find it out? So what you would end up here is very simple math here. Okay, L will be equal to, any idea?
Root k0 square plus k1 square.
Right, very good. Did you work it out now?
Sir, it will be root, I think, not 1 by root.
Huh? L will be equal to 1 by root. Try it out yourself. I'm just giving you L directly here. And theta is very easy to find out. Theta equal to
Okay.
tan inverse of Shashwat has been telling it from the last class. Now he's silent.
K1 by k0.
Yes. The same answer you are telling, right, Shashwat?
Yes, sir.
Okay, good. So that's all. These are the two values you would get. Very, very important things. So what it is saying is, you see, doing it is also very simple. This is theta. What is this value? This angle, how much? Maybe
90
one
minus theta.
90 minus theta.
theta. What is this angle?
Theta.
Theta.
That's it, theta. This is if this is 90, this is also 90, right? This is 90 minus theta, so that is theta. One is you take this, the whole thing you take tan theta. Okay, this is 1 by k1 here. Okay, again got disappeared. So you know one tan theta there. Okay, so if you take tan theta there, that is giving you k1 by k naught here. Now this whole length you know. Now you take this in order to find out this length, you take compute tan theta here, that will give you one equation. You take one more equation by taking this triangle and compute tan theta, that will give you this length. You add those two equations and you would arrive at this length L. Okay, because in both of them you would be getting this length L. Okay, from that you would arrive at this expression. I'm sure with that you would be able to work that out. So the conclusion here is the periodicity is oriented at an angle of tan inverse of k1 by k naught. Okay, that's where your periodicity you have to do in that direction, and the periodicity is 1 by square root of k naught square plus k1 square. That's all. Is it clear to everyone now? Yeah, this part you just work it out, that this length will be equal to 1 by k naught square plus k1 square and theta equal to tan inverse of k1 by k naught. Very simple math here. Just you need to look into those right angle triangles. 3 right angle triangles you take and you are done with it. So maybe I'll stop here. We will see few examples of so you spend some time again, okay, going back, you play with k0 and k1. Now, in addition to what you were asked to do earlier, if you had done it already, it's good. Otherwise, what you do that again, looking at expecting from varying your k0 and k1 manually, see how the graph should look like and check if it is looking like that or not. And by looking at the graph also, you should be able to say where in the Fourier domain where you would be having impulses. And then you try the other way also. Assume that you have a cosine there on the Fourier domain. So how does it look like? So with frequency, by just looking at some graphs, okay, I'll maybe quickly show you few here. See, you should be, for example, by looking at it, you should be able to say where its impulse would be. Okay, in which direction it is, whether it is an increasing frequency or decreasing frequencies here. Okay, in which direction they will be. How? So I could ask you things like, suppose given to this versus this, or in the same thing, if I am increasing this versus, you take these two. Okay, I might not give you absolute values, but you should be able to say whether they go far or near. in which quadrants they would be, that all you should be able to figure out. This absolute clarity you should be having, some intuition you should be having, even without doing anything on pen and paper or programming anything. By just looking at these graphs, you should be able to say how its frequency spectrum would look like. So if I'm increasing frequency, how it would look like. If I'm increasing kx, what would happen. If I'm increasing k naught, or if I'm increasing k1, what would happen. So take some time to contemplate on these aspects. Okay, so I will stop here. Anyway, this PPT presentation, we will go in more detail in the next class, or maybe I would make now, given that this has been done, now I will make a video for that also. Okay, so is that clear? Any questions? No one have any questions today? I think the strength has dropped a bit. 7, I think usually 30 are there, today 23 are there. Anyways, I will, this hope still it is getting recorded, so I'll upload it. But meanwhile, is it clear so far what we discussed? Devian, was that clear?
Yes, sir.
Okay, good. Anyone from MTech students? Is it clear to you, the MTech students?
Yes, sir.
Okay, good.
Yes, sir.
So please spend some time, unless you spend some time with sines and cosines. Okay, you should allocate it some time and go through it, and then only things would become clear and will become obvious to you. So every time you should not be looking, the moment you are seeing, you should not be putting 4 or 5 equations there. Okay, this is cos, k naught is positive and all, then it should be almost like instantaneous for you. If you spend some time experimenting with it, trying to get some insights into it, then it will become instantaneous for you to answer any of these things. Okay, so if it is clear to everyone, we'll stop here. I'll just stop the recording part here first.